Hello everyone. A few videos ago, we discussed and demonstrated the Trainer Black model. In this video, we continue our discussion on active portfolio management. We had noted before that mean variance optimization has a few problems. For example, in Markowitz's paradigm, optimal portfolios are highly concentrated and very sensitive to provided inputs. Empirical evidence also indicates that a small change in expected returns can cause a drastic change in portfolio composition, so we get some weird portfolios sometimes. The Black and Litterman model, proposed by Fisher-Black and Robert Litterman, it is represented as an asset allocation model, but it is essentially a model to forecast expected returns. And once we know expected returns, we can use standard optimization techniques to arrive at the optimal portfolio. What Black and Litterman do is what we can call reverse optimization in order to arrive at an estimate of implied equilibrium excess returns. They also allow us to incorporate our views about various stocks or assets that comprise our portfolio, and also our confidence about our views to generate the expected return vector. Let us deal with these ideas. First, let us consider the notion of implied equilibrium excess returns. Let us begin by writing our investors' utility function. Let us say our investors have this utility function, so U for utility, and equal to our expected returns, which is W transpose times R, minus, we are now going to penalize the risk by subtracting from our expected returns half times the risk aversion parameter, or the price of risk, denoted by A here, times W transpose times the variance covariance matrix times W. This thing captures our variance of the portfolio. So we have this utility function, and we want to maximize this subject to the constraint that the sum of all weights should be equal to 1. To maximize this utility function, we are going to take a partial derivative of U with respect to W, which is going to give us, from here we are going to get R, and from this term we are going to get 1/2 times 2, because W transpose times W is equivalent of writing W squared. So 2 times the risk aversion parameter A times the variance covariance matrix S times W. So this 2 is going to cancel out with this, and we are going to have here R minus the risk aversion parameter times the variance covariance matrix times W. In order to maximize the utility, we set the derivative equal to 0. Now what Black and Litterman did was, rather than solving for optimum weights, they argued that weights are already observed in the market, and therefore we can compute them using market capitalization. What they did therefore was to reverse the problem. They solved for R from this equation here. So if we do that, what we are going to see is that R is going to be simply equal to the risk aversion parameter A times the variance covariance matrix S times the market weights. This risk aversion parameter, or the price of risk, can also be written as the excess return on the market divided by the variance of the market. Now if we are in agreement with the excess returns thus generated, we should hold the market portfolio, because in the absence of any other view, these returns would take us back to the market weights. Let us call these implied equilibrium excess returns as a vector, and let us give a name to that vector. Let's call it vector pi. So pi means our implied, let me write it out here, implied equilibrium excess returns. So that we don't have to write this whole long thing again and again, we can simply call this vector vector pi. Now let us introduce our views about the stocks that comprise the portfolio. Well, we can have absolute views, like for example the return on Google's stock will be 2% in the near future. We can also have relative views. For example, the return on Amazon's stock will be greater than the return on Apple's stock by 1%. In practice, relative views are more common, and we will use them for our discussion. Let us consider a 3-asset portfolio comprised of 3 assets. Let's give them names. Let's call them assets A, B, and C. We believe that the return on asset A is going to exceed the return on asset B by, let us say, 1%. We can also say, let's say we have another view where we say that the return on asset C is going to exceed the return on asset A by, let us say, 0.5%. So what we have now is that we have 2 views which can be expressed as a vector. Let us see how that vector is going to look like. Let me make some space and write that vector here. Let us first of all give a name to that vector. Let's call it our views vector and give it a name Q. So let me write it here. Q is our views vector. And we can write this vector as simply equal to, well, this 1% here, so we write 0.01, and this 0.5% here, so we can write 0.005 here. So this is our views vector, in this case a 2 by 1 vector. In general, the views vector Q will be a n by 1 vector, where n would be our number of views. The problem is that by looking at vector Q, we don't know what the views are about. So what we need to have is a matrix which is going to establish a link between our views and what the views are about. Let us call this matrix matrix P. And because it's going to establish a link, let us give it a name, link matrix. So how do we write this link matrix now? Let us say each row represents a view. So we have 2 views in our case, in our example. We have view 1, we have view 2. Well, this is the first view and this is the second view. We also have 3 assets. So let us write the assets in columns A, B, and C. So we are going to have this matrix, which in this case is now what? A 2 by 3 matrix. The question now is, what are going to be the elements of this matrix? Well, for each positive view we can write a 1, and for each negative view we can write a -1. But do keep in mind that the sum of relative views should be 0. What are our views? We believe that the return on asset A here is going to be greater than the return on asset B. So we are positive about asset A. So in the row for the first view, we can write a +1 below A. And we are negative about which asset? We are negative about asset B. So we can write a -1 here. The first view doesn't talk about asset C at all, so we can write a 0 here. Now the sum of these views is going to be 0. Likewise, we can fill the row for the second view. What is our second view? We are positive about asset C, so we can write a +1 for asset C. And we are negative about, relatively speaking, we are negative about asset A, so we can write a -1 here. And the second view doesn't talk about asset B at all, so we can write a 0 here. So this becomes our link matrix. We can say this is matrix P. Let us now focus on risk. It is pretty obvious that whenever we have expected returns, well, the name expected, the term expected itself implies that there is going to be some uncertainty about the issue that we are talking about. So if we are talking about expected returns, there is going to be an uncertainty about them, which we can represent through the variance covariance matrix. We have used a notation for that before. We have called the variance covariance matrix as S. If we wish to now have a measure of confidence about our expected returns, well, what are our expected returns? The expected returns, the implied equilibrium excess returns, are given to us by this vector pi. So if we want to have a measure of confidence about our expected equilibrium returns, we can express that confidence by simply writing S inverse, because if S, which is the variance covariance matrix, represents uncertainty, S inverse is going to represent the confidence that we have about our estimated implied equilibrium excess returns. Likewise, the views that we have are just views. They are not facts. They are not set in stone. Therefore, there is an uncertainty about the views also. So if views are represented by this vector, vector Q, there is also going to be a vector for the error term. Let us write down this as follows. Let us say we have views which are represented by vector Q, but because we are not 100% sure about our views, there is going to be an error component. Let us write the error as the epsilon. So we can write this for our example. We have two views, so we have an element Q1 in that vector and an element Q2 in that vector, and both of them have some error term because of the uncertainty. We are not fully sure about our views. It's just an opinion. So if we fill in the numbers that we assumed, we have something like this: 0.01 for the first view, 0.005 for the second view, and we have then this vector which captures the error about our views, the uncertainty about our views. Now we are going to make an assumption. We are going to assume that the error terms are normally distributed, which we can write as this. We are writing the characteristics of this vector, epsilon 1 and epsilon 2, normally distributed. So we can write they are normally distributed with a zero mean. So there is going to be a zero mean and some variance, which we can write through this matrix. This looks like a W, but actually I wanted to write here the Greek letter omega, which is slightly curved. So let me try to make it curved a little bit. Alright, so this represents our uncertainty. Well, this is our zero mean for the error, and this is the uncertainty. This uncertainty matrix, which in our case now is a 2 by 2 matrix, we are going to give a general name to it. We are going to call it omega. Well, I'm not too good at drawing Greek letters, so, well, this is omega for me. Alright, so this is an n by n matrix and represents the uncertainty about our views. The problem is that there is no one best way of computing the elements of this matrix. Black and Litterman suggest, however, that the elements of the matrix omega, which are capturing the uncertainty about our views, can be calculated as a scalar, which they write as tau, times the link matrix, times the variance covariance matrix, times the transpose of the link matrix. Now tau is just a scalar and it is just as abstract as the omega. Black and Litterman have used a value of 0.025 in their paper sorry, this is not for omega, this is for the tau. 0.025 for the tau. And other people, other researchers have simply used a value of 1. A value of 1, well, it is convenient to use, so we are also going to work with a value of 1 for tau. It's just a scalar. In any case, if omega represents the uncertainty and we want to have a measure of confidence about our views, we are going to simply write the measure of confidence about our views as the inverse of the omega. So that gives us the measure of confidence, how confident we are about the views that we have. Okay. So we have introduced a lot of items. Let us collect them all in one place so that we can see what is the list of our inputs for our 3-asset portfolio. Let me make some space and write a summary of what we have discussed so far. We have tau, which we have assumed to be equal to 1. This is a scalar, and we have assumed it to be equal to 1. We also have the vector pi. In our case, because we are dealing with a 3-asset portfolio, it's going to be a 3/1 vector for our implied equilibrium excess returns. We also have S, which is our variance covariance matrix, which is going to be of the order of 3/3. We also have a vector for our views, which we have named Q. It is a 2/1 vector. We also have a link matrix P, which is, we had 2 views, so 2 rows by 3 assets, so 3 columns, so we have a 2/3 link matrix. And we have omega, which is the uncertainty about our views, and we saw before that it was a square matrix, 2/2 for our case. Now what the Black-Litterman formula does is that it gives us an estimate of excess returns by calculating a weighted average of 2 items. That is all the Black-Litterman formula does. It's simply a weighted average of 2 items. So what are those 2 items? Let's write them down. It is a weighted average of pi, which is the implied equilibrium excess returns. What is the second item? The second item is our views, which is captured by our Q vector. So we are going to have to compute a weighted average of these 2 items here. The question is, what are the weights? Well, the first weight is the confidence about the pi, and it is represented as this scalar tau times the variance covariance matrix, and because we are measuring the confidence, we take the inverse. The second weight is going to be related to our views, how confident we are about our views. That's going to be the weight. So the confidence is going to be represented as omega inverse, and we said that just by looking at the vector Q, we didn't have an idea about what the views were about, so we also have to have a link matrix. So what we are going to have to write here is a transpose of the link matrix. You may ask why transpose. It's just to facilitate matrix multiplication. So what we basically have, let's write down the weighted average then. What we have is, well, we write the first weight, tau times S inverse times pi, which is our vector for implied equilibrium excess returns, plus we write down the second weight, P transpose times omega inverse, and we multiply this by our views, Q. So, well, what is this then? This is weighted pi. And what is this? These are our weighted views. So we can write weighted Q. Well, this here is the weight on pi, and this item here is the weight on Q. If you have seen the Black-Litterman formula in your books or any literature before, you will realize that the term that we have just written here, this one here, this entire term, is the second term in the formula. Where does the first term come from and what does it do? Well, you will realize the fact that the sum of all weights must be equal to 0, and that is all that the first term of the Black-Litterman formula, which is this, let me write the first term down here, tau times S inverse plus P transpose times omega inverse times P, and we take the inverse of this whole thing. So when we multiply this second term, let me write here, this is the second term of the Black-Litterman formula. So when we multiply this second term by this term, let me call this the first term of the Black-Litterman formula, we are ensuring that the sum of all weights is going to be equal to 1. That is all this first term does. We are going to demonstrate this through a simple example in another video. For now, let us conclude by writing the complete Black-Litterman formula. What we are writing here is that our excess returns are simply equal to, well, the first term multiplied by the second term. P transpose times omega inverse times Q, and that is the Black-Litterman formula, where this part here is simply a weighted average and this part is ensuring that the sum of all weights is equal to 1. The end result of the Black-Litterman formula, in our case we have a 3 asset portfolio, so in our case the end result is going to be a 3 by 1 vector of expected returns, which would represent a mix of equilibrium returns, which we estimated by using market weights before, and our views. Let us see how we are going to arrive at that vector. Well, let us see. Let's work with the first term here. We have S here and the inverse of S. This is going to be a 3 by 3 matrix. Plus, we have the transpose of P. What is the order of P? The order of P, let's scroll back up and see. I believe it was 2 by 3. So P here, which was our link matrix, was of the order of 2 by 3. When we take the transpose, we are interchanging the rows and columns. So we can write this P transpose as a matrix of order 3 by 2 multiplied by omega inverse. Omega was a 2 by 2 matrix, and multiplied by P, which is 2 by 3. So let us see what we get here. 3 times 3, 3 by 3, plus if we multiply out these two matrices, we are going to have a 3 by 2 matrix multiplied by this one here, 2 by 3. So what we get, 3 by 3 plus, well, if we multiply out these two matrices, we are going to have another 3 by 3 matrix. So we are going to have a 3 by 3 matrix from the first term of the Black-Litterman formula. What is the second term going to give us? Well, S inverse 3 by 3 matrix multiplied by pi, which is what? 3 assets, so it's a vector, 3 by 1 vector, plus P transpose. P transpose is 3 by 2. Well, I'm running out of space here. Times omega inverse 2 by 2 times the Q vector, which is our views vector 2 by 1. Well, I don't have any space left to close this bracket. Okay, so what we get, if we multiply out these two matrices, what we have is a 3 by 1 vector, plus if we multiply out these two, we are going to have a 3 by 2 vector, and we have this one here 2 by 1. So what we have now, 3 by 1 vector, plus if we multiply out these two, now we are going to have another 3 by 1 vector. So we get a 3 by 1 vector here. So this is the matrix that we get from the first part of the Black-Litterman formula. This is the matrix that we get, this is the vector rather, that we get from the second part of the Black-Litterman formula. So the complete will be 3 by 3 times 3 by 1, which is going to give us 3 by 1 vector in our case. Well, this is all I wanted to tell you in this video. See you later.